All right, guys. So today's lab is on gas properties and ideal gas law. So in this experiment, we're going to explore how quantities like pressure, volume, number of molecules, or number of moles, right, are related to one another. So we're going to look at sort of like, let's say, thermodynamics properties. The idea is that if you have a container and you have molecules in this container, so what we have here is the N is the number of molecules. Number of molecules. So let's say you have n number of molecules in the container. So some of the state variables when you describing ideal gas law, are the volume of your container. Oops. P is then the pressure, and N is the number of molecules. A lot of times, one of the things we can do here is if we have, a certain amount of molecules, let's say Avogadro number of molecules. That means, for example, if our number of molecules is 1.602 times 10 to the 23, then we can, let's say this is n, right? So let's say you have this many molecules. All right, my bad. It's 6.02. All right, so 6.02 times 10 to the 23 molecules. Then we can say that this is defined as Avogadro number of molecules, n sub a. So this is basically Avogadro. So Avogadro's number. And to simplify sometimes, our calculation, we can represent that this to be equal to 1 mole. So N is then number of mole. That means 1 mole is equivalent to 6.02 times 10 to the 23. That means we can say that the number of moles is basically based on this Avogadro number. So if you have, let's say, 2 moles, and that means that means you have 2 times the Avogadro number of molecules. Okay. Again, N is the number of moles. So that means 1 mole is equivalent to Avogadro number of molecules. Okay, Avogadro number of molecules. All right, so let's say then what we have here is those are our state variables: volume, pressure, then number of molecules, or basically number of moles. Okay, and what we're going to do here, we're going to explore how those things are related to one another, and basically verify the theory, because the theory says that when you have a container with some n number of molecules, one of the things we can do here is we can there's also a temperature. I should not forget that. So T for the temperature. And then the temperature is in Kelvin rather than Celsius. So generally, when you talk about temperature in the ideal gas law equation, it's always in Kelvin. So that means those variables, right, are known as the macroscopic variables of ideal gas. So macroscopic means, right, so M for so macroscopic. So macroscopic state variables. All right. So the macroscopic means that basically sort of a large scale, not at the atomic level, but we're looking at a big picture. Okay, so you have a container with it has a volume, it has a pressure, and so it's not like individual particles and things like that, which is the kinetic theory of gases. That but this sort of like a general big picture. All right, so then our experiment is going to then investigate how those things are related to one another. That means putting those variables together. So you have volume, you have pressure, you have temperature, and you have N, which is then the number of moles, how those things are related. Again, it's not either number of moles or number of molecules. We can, they are pretty much, same, let's say, variable. So exploring those state variables, how these, variables are related to one another. Now, in terms of, for example, starting with pressure. So question is that how is pressure related to the volume? Okay. So the theory says that a pressure is inversely proportional to the volume. That means if you change the volume, it affects the pressure, but in such a way that increasing volume gives you decreasing pressure. Okay. Now, we're going to be exploring that. We're going to do two experiments. One, we're going to look at as observation. Second one, we're going to do an experiment, take data and make measurements and graph and see that relationship. So we're going to explore this. So like, let's say condition one, is pressure proportional to 1 over volume? Also, another, a statement is that pressure is directly proportional to the temperature, which means that if you increase temperature, pressure increases. So we're going to explore that as well. And then the third property we're going to explore is that pressure is directly proportional to, N number of molecules or number of moles. That means if I have a pressure gauge here, okay, if I increase the number of molecules, theory says that pressure will increase. Okay. And if I put this on some kind of, let's say, hot plate, so like, let's say hot plate, and pump some heat, then according to this condition two, the pressure will increase. And if I have a way of changing the volume, shrinking the container, or making it bigger, right, then the pressure also changes, but inversely. Okay, then the ideal gas law equation then puts them all together. That means it tells us that, all right, pressure is proportional to temperature, proportional to number of molecules, but inversely proportional to volume. Okay, so now, then one thing we can do here is we can look at in terms of going from proportionality sign to equal sign, which is generally introduced as a constant. So the ideal gas law generally comes in two different equations, two different versions. One is in terms of number of molecules, the other one is in terms of number of moles. Okay. So the first equation is pressure is equals to, going from proportionality sign to equal sign, as I say, right? So it's equals to temperature times number of molecules divided by the volume. That's how, it's proportional to those things. And then we introduce a constant. And that constant for this equation is known as a Boltzmann constant. Generally, this equation written as moving V to the other side becomes PV equals, NKBT. So this is, let's say, then one version of the ideal gas law. The other one is pressure is equals to, so the same thing, right? Temperature, but this time I'm writing in terms of number of moles, then divided by the volume. This time the constant, when you replace number of molecules with number of moles, is actually R, which is a gas constant. So in this case, this equation becomes, again, PV, moving V to the other side, and RT. That means you have those two versions of this ideal gas law using two different, sort of like a constants. And those constants are related to one another. So in a way, you can kind of like, let's say, derive one from the other one, because let me write this here. KB, the Boltzmann constant, is equals to R over Avogadro number of molecules. So that's why, for example, in the first equation, when you have N KBT, okay. So remember when I said that number of molecules and number of moles are related such that the number of molecules is equals to number of moles times Avogadro number. That means if I do the ratio of number of moles over Avogadro number, sorry, number of molecules, of total number of molecules over Avogadro number, that's what the number of moles equation represents. So that's a ratio of a number of total molecules divided by Avogadro number of molecules. That means if in the first equation of the ideal gas law, I replace the KB with R over NA, you can say, right, then N over NA is basically nothing but the number of moles, so nRT. That means, you go from one equation to the other one. That's why they're the same. They're pretty much the same. You just, the idea here is that you are using either this constant or this, so like, let's say the R, right, as a constant, and basically replacing number of molecules with number of moles, and KB with the R. We're not really using those quantities here. We're not going to be using any of the Boltzmann constant or the gas constant, but just in case, you know, refer to your let's say textbook for the values of those constants. But let me put this here. So KB is equals to 1.38 times 10 to the negative 23 joules per Kelvin. So Kelvin to the negative 1. That's a Boltzmann constant. And then what we're going to do here is the R is, which is the gas constant. You can then, in a way, write this two different ways, depending on if you're doing in terms of, let's say, pressure, which is in Pascal, and volume, which is in cubic meters, or let's say if you're doing pressure in ATM and Pascal is in liters. So you kind of have two different values for that, because 8.1314. So this value is in terms of joules per Kelvin and mole. Okay, joules per Kelvin per mole. Or you can say the R here can also be written as 0.0821 liters times ATM per mole Kelvin, depending on, let's say, what you have on the left side. So if this is in, let's say, Pascal and cubic meters, then you use the first version. If you have it's in ATM, which is another unit for pressure, right, and liter, which is another unit for the volume, then R becomes into 0.082. Anyways, again, as I said, right, we're not really using that in this particular lab, but this is sort of like what we have. And one of the few things we can explore here are the properties, right? So how those things relate to one another. And to do that, we're going to be looking at, for example, remember, so pressure is proportional to let's say number of molecules, temperature, and volume. So we're going to see individually what the let's say how the pressure affected by the temperature, and how the pressure affected by the volume, and how the pressure affected by the number of moles. In order for us to do that, we need to look at sort of like a specific laws, because that means we have to look at one variable effect at a time. Okay, so in order to see how the pressure affected by the temperature, we need to then keep everything else, other two variables, constant. That means, for example, number of moles or number of molecules and the volume, keep them constant, and only change the temperature and see how the pressure changes. So, all right. So, for example, in terms of then, there are a couple of laws that you guys can also explore. So, for example, how the pressure proportional to, for example, let's say volume. Okay, so remember, so this is pressure inversely proportional to 1 over volume. This is we will do when number of moles are constant. That means we're not changing number of moles or number of molecules, and also temperature is constant. That means, for example, T is constant. Okay, and we assume that N is also constant. So this is known as Boyle's law. That means Boyle's law explores the relationship between pressure and volume when the temperature is constant. Then we can also look at when the pressure, how the pressure depends on the temperature, which is, theory says that they're directly proportional. So then this is basically keeping then the volume constant and number of moles constant. So this is known as Gay-Lussac's law. All right. That means we're going to be exploring those laws in terms of being able to do that. Because if you want to see how the pressure relates to volume, you cannot change other things as well at the same time. So you only want to change volume while keeping other things constant. So that's why we're going to be using Boyle's law that keeps temperature constant and Gay-Lussac's law to keep volume constant to see how the temperature affect the pressure. All right. So I think we're ready to go to our experiment and see how the experiment observation and experimental measurements can help us verify, these relationships. All right, so let's go and there you go. All right, so our experiment has two parts. One part, because the learning objective is to design an experiment to measure the relationship between pressure, volume, and temperature. Create graphs based on the prediction and observation. Make qualitative statement about the relationship between pressure, volume, and temperature using molecular models. So I'm giving you two types of experiments. So like let's say one is a simulation where we're going to be observing, let's say those relationships. The other one is and we're not going to make any measurements here. Mostly like let's say observation and answering some of the questions, for part one. All right, so to do that, basically you're going to run the ideal gas law simulation. So you're going to click on this one. So you will then see what we have here is a container where there is a pressure gauge and there's a thermometer measuring the temperature, pressure gauge measuring the pressure. A way for us to, let me kind of talk about it like this, right? So this is the pressure gauge measuring pressure. So you're going to be able to see that in terms of how pressure changes. This is the thermometer that's going to give you increase, decreasing, let's say the temperature. This is the source of changing the temperature, increasing, decreasing temperature. You're going to, the hot source or cool bath and things like that to change the temperature. There's a pump over here that's going to pump molecules into the container. And also we have a way of changing the volume. So just basically push it here. We're going to then change the volume. All right. So those are the things we're going to be then exploring. And your goal here is to explore those, Boyle's law and Gay-Lussac's law. That means how the pressure changes based on those variables. Again, it's relatively straightforward. For example, what we do here is you can see right now the pressure is zero. Let's say pressure is zero because one of the things we talked about here is there are no molecules. So N equals zero here. And then we know that pressure is directly proportional to N. Well, if N equals zero, then the pressure should be zero. And that's basically what we can explore here. Well, what happens here then if we pump more molecules? So you take this pump and just pump molecules, and then you can see, eventually the pressure starts increasing. All right, so you can observe, you're gonna, let's say, pump more, take out less, and then this is how you can take out. So you open this and the molecule can escape. So then you can just basically decrease number of molecules, right? And then, pump more to increase number of molecules and observe the pressure gauge to see what happens, right? What happens to the pressure when you increasing, decreasing the number of molecules. So this is basically in terms of the relationship between number of molecules and number of moles to pressure. Then we can look at in terms of, let's say, Boyle's law. Remember, Boyle's law, we're keeping the constant temperature, but, changing the volume. That means if I take this container and I make it bigger, I look at the pressure. I make it even bigger, right? Increase the volume. I can see, right, what happens then, to the pressure. Or I make it smaller and smaller and smaller and smaller, and then you can see, right, what happens. Your goal is to do this observation and then explain everything, write it down in those questions, let's say, not just, okay, pressure increases and things like that. Why? What's the reason, and things like that. Remember, so the idea here is that you have the molecules, right, colliding with the wall, right, and the pressure is based on the collision with the, with the walls of this container. And then the question is that then why increasing or decreasing the volume makes the pressure decrease or increase. Let's say you're going to need to try to explain all of those things to me. All right, so let's then, in terms of, you can see, right? So in this case, we change, if I click this temperature constant here, right? So if I use this one, it uses Boyle's law, which means that right now you can see, right, the options here just disappeared everything. So that means I'm not changing the temperature. It's 248, and then regardless what I do to the volume, the temperature remains constant, and I can see direct relationship between pressure and the volume. For the next part, we can then do the opposite. uh, Keep the volume constant. So if I click the volume, see the options to change the volume disappeared, and I can change the temperature. To do that, you can see, right, the options here came back, right? The options here came back. So then I can, go to heat, increase temperature, and then I can see what happens to the pressure, or then I can decrease temperature, put a cool bath, and then I can see what happens to the pressure. I think it's a really nice, well done simulation that allows you to, see all those relationships. Because when you see PV equals nRT, right, sometimes it's not very obvious, like why, and how they're related. Just not just simply mathematic, right? You can see the physical, let's say, changes as well, like this. All right. So this part, I think, relatively straightforward. You should be able to just look at this and get all the um, relationship of the pressure to the other quantities, and then just answer this, straightforward, simple questions. Let's go to the next experiments. Now we're gonna do the, actual experiment, not a simulation, actual experiment, and we're gonna then explore that as well. So this is a little bit more sophisticated exploration. So we're gonna look at in terms of, you can see, right? So in this video below shows a small plastic lid dipped in bubble soap and placed in a glass chamber with vacuum pump attached. A pressure sensor measures the air pressure inside the chamber. When the vacuum pump is turned on, the bubble forms from the air trapped in the plastic lid. As the pressure in the chamber decreases, because we're removing the air, right? The bubble expands. And your task here is to design an experiment to find the mathematical relationship between the volume of the bubble and pressure in the chamber. So we're going to watch the video and use the instructions to collect data, and we can then actually graph this data and measure um, some of these quantities. All right, so here's then the experiment. So let's say you can write trial 1, 2, 3. So experiment is really straightforward. So, that's a soap bubble, you close it, and then you start removing the air. So right now that's the pressure, and you start removing the air. You can see, right, then the pressure inside decreases, and then the bubble starts increasing, right? So you create a bubble and then starts increasing, and you want to see that how the volume of the bubble related to the pressure inside the container until it pops. So your goal would be to do some measurements. So it says design a method to determine the relationship between pressure in the bubble and the volume of the bubble. Okay. So in a way, it's not pressure in the bubble, but pressure sort of like, let's say, in the container, right? Because this is a measurement of the pressure in the container. So you can assume that the pressure in the bubble is the same as the pressure in the chamber and is displayed on the phone. So it's to the right of the chamber. So the iPhone, right, basically gives you the pressure. So write a description of your method, including what quantities will you measure, what additional calculation will you need to do, and things like that. So I want to, so like, let's say, um, this is like you coming up with an experiment. Okay. But, I'm going to give you, like, let's say, some ideas in terms of what to do. So let's say some of the tools that are available to us, just one, which is a meter stick, sort of like a ruler. That means, in a way, one thing we can do here is measure, because you kind of restricted, right? Measure some kind of length. Now, what length can we use to measure, right? Well, think like this. What we have here is, okay, say the bubble starts increasing the volume, right? That means one thing we can do here is we can measure how the volume changes as a function of pressure. Okay. That means that's one thing we can do, right? We can't measure volume here directly, But one thing we can do here is we can measure the diameter of the bubble. That means going back when, right now, you start this and you start generating bubble. Now, here I can't measure the diameter or the radius, right? So I can't measure because I don't have the spherical shape yet. So you wait until it has a spherical shape, so maybe something like this, then maybe you start measuring. Okay. Then once you kind of have the spherical shape that you can measure let's say have a reliable measurement of the diameter, then you basically start measuring things. And you're going to have a data table here, right? It says use the data table to collect and analyze data. So measure the pressure and the diameter of the bubble. That means you basically need to have two measurements, which is the measurement of the pressure that you see in an iPhone, right? Let's say, and also be able to measure the diameter of the bubble as it's forming. So let's say right now, one of the things you can see here is this is basically where I already see the shape. That means it's already spherical, so that I can go from one end to another and measure, let's say, the diameter. Okay, that means one thing we can do here is we can say that we need measurement of pressure. Pressure has units of, in this case, you can say, right, you were given in terms of ATM. It's fine to keep it in ATM. And this is just P for pressure. And then we're going to use the diameter. And then we're given in terms of centimeters. That's fine to keep it in terms of centimeters. So D for the diameter. Now, then you basically measure, right? So let's say I'll give you a few measurements. So 0.439. So let's say when pressure is 0.439, then what I get here is what about 2.9 centimeters. So give or take. So for example, I can just zoom in here and I can see that about 2.9 centimeters for the diameter. All right, so let's say here I do 2.9 centimeters. And then I go and look at in terms of some later time. And I can stop and I can say, all right, so when it's 0.347, and I want you to make around 9-10 measurements, around 9-10 measurements. So I can then see that right now the diameter has increased a little bit, so it's maybe about 3.2 or something like that. So you can come and say, all right, so 3.2. By the way, see, there are different number of trials, so I'm going to make measurements for the trial one. Do not use trial one then when you're doing. So use the second one, third one, fourth one, or fifth one, right? Because I don't want you to just copy my measurement values. So just try to get your own. So let's say right now I can go a little bit further and 0.248. So 0.248. So then let's see what's the measurement there is. So I would say it's roughly 3.6. So about 3.6. And I think right now I'm good enough because you again, you need to make up to about 8 to 10 measurements. More measurement you have, better generally your experimental data. Then it says basically measure the pressure and diameter and then calculate the volume and then 1 over P. So the question is that why 1 over P? Because our goal here is to be able to get, remember, so if you want to find how those things are related, so if the pressure is directly proportional to volume, we're going to get a straight line. But we know that it's not directly, it's inversely proportional to volume. Okay, it's inversely proportional to volume. So you can do two things. For example, if you rearrange, means that the volume is also inversely proportional to pressure. So just one thing you can do. So in a way, they're like you can do two things. You can do pressure versus 1 over volume. So instead of 1 over P, just calculate 1 over pressure, 1 over volume, and then plot pressure versus 1 over volume, or then have volume and then calculate 1 over the pressure and then plot volume versus 1 over pressure. All right, so you're gonna, our goal here is to see if it's a straight. Our goal here is to see if it's a straight line or not. Okay, that means, for example, if I go and calculate the volume, so you need then 2 more columns. So to the right, another one to the right. So here, let's say we have the bubble volume. Okay, so the unit is going to be centimeter cube. Okay, so V for the volume, and think like this. You don't need to directly, calculate each individual one. You can have a formula. So change the formula. Remember, the formula for the volume of the sphere will be 4/3 times pi r cubed. Okay, so 4/3 pi r cubed, or you just basically can do in terms of the diameter, right? So let's say do either in terms of diameter, or maybe if you want, you can just have another column here and say this is then radius in centimeters and r for the radius. All right, so then what is the radius? Radius is half of the diameter. So write a formula, and then it just takes half of that. Then here, bubble volume formula will be 4/3 times pi. We don't have pi, but we can write it as 3.14. Then times, then r cubed, like this. And that's our volume. Okay. And then here you can say it's 1 over pressure. So that means is 1 over ATM. And, no variables there. So then I go and say, right, so this is just formula will be, 1 divided by the pressure that I have. There you go. And that just basically takes the pressure and get the inverse of that. The idea here is if you are then plotting volume, bubble volume versus, see, if you do 1 over pressure, you're going to get a data like this. Okay. But if you do in terms of 1 over pressure, you're going to get a data like that, which should allow you to see that they are proportional directly. Okay, and you can see that they are directly proportional in terms of that. It should be a straight line. If you do volume versus 1 over P or pressure versus 1 over volume, you should get a straight line. And then the rest of this is just basically equations based on all of those, observations of your graph and the relationship between bubble volume and the pressure in the chamber, right, based on your experiment. All right, guys. So if you have any questions, let me know. But hopefully you will learn, I think, quite a lot by looking at this, both simulation and experiment, because you see both observation and experiment. And the take from this lab is to be able to see how the pressure, proportional or related to the volume, temperature, and the number of molecules.